it would be in there, but I will make sure that I don't have it anywhere else. But you took it on Wednesday last week? Okay, I'll take a look. I don't know. I'm sorry. All right, let's get started. So today we're talking about 10.2 on sequences, and specifically we're starting to compute limits of sequences. So any questions that I can answer for you? Yes, sir.
Number 55.
55. Okay, so we have sequence -1 to the n, 2 to the n. Okay. So 55 is the sequence -1 to the n divided by 2 to the n. And the directions are find the limit of the sequence or determine that that sequence diverges. Okay. So if we're finding the limit as n goes to infinity of -1 to the n over 2 to the n, well, what is happening up here? Maybe a good idea would be, let's just write out a few terms of the sequence and kind of get a feel for what's going on. So if n is 1, what do I get? Yeah, -1/2, right? -1/2. If n is 2, what happens? Yeah, so I get a positive because this just flips the sign every time. And on bottom I get 4. So 1/4. And then what would I get? A negative, because now this is cubed. And on the bottom I get 2 cubed, which is 8, so -1/8. Then, then positive a 16th, then negative a 32nd. And the question is that getting close to something? Yeah, and what it's getting close to, right, is 0. Yeah, so we could say that that one is 0. Sound good? Other questions?
We do 22.
Sure. 22. Okay, we've got k over square root of 9k squared plus 1. K over the square root of 9k squared plus 1. Okay, so we're wanting to take the limit as k goes to infinity of k over square root 9k squared plus 1. So we're having to remember some of our tricks from Calculus 1. And one of the tricks here, there's a couple ways we could go with this, because if I plug in infinity for k, I suppose that I get infinity over infinity, right? So I could use L'Hopital's rule if I wanted to. I'm not sure that that's like my favorite thing. Typically what I would do is I'd say, well, what's the highest power of k on the top and on the bottom? And on the top, it's obviously to the first. On the bottom, it's squared, but square rooted. So it's kind of sort of like the first power. So what I could do is divide the top and the bottom of the fraction by k. All right, so let's try that and see what happens. So I could say this is the limit as k goes to infinity of, if I divide the top by k, and really when I say divide the top and the bottom by k, what am I really doing? I'm really multiplying the top by 1 over k, and I'm multiplying the bottom by 1 over k. So I'm multiplying by 1 over k over 1 over k, which is otherwise known as 1. So really I haven't changed anything by adding these k's to the top and the bottom. But now the top becomes 1. And the bottom, I could put the k inside the square root. And if I did, it would be a k squared. So I could write this as the square root of 9k squared plus 1 over k squared. Now I could break that into 2 fractions. Sorry, I forgot my limit. K goes to infinity. So I've got limit as k goes to infinity of, on top I still have 1. On bottom I have the square root of 9k squared over k squared plus 1 over k squared, which is k squareds here cancel, and I get the limit as k goes to infinity of 1 over the square root of, this is just 9, and this one is 1 plus 1 over k squared. Now we could let k go to infinity and life is sort of wonderful. So because when k goes to infinity, 1 over k squared goes to 0. So this thing just becomes 0, and I'm just left with 1 over the square root of 9, which is a third. So if I would have gone through L'Hopital's rule, if I take the derivative of the top, I get 1. If I take the derivative of the bottom, it's kind of a mess, right? So L'Hopital's rule might work as well, but it seems harder. So those 2 ways would both work. Other questions?
Is it fine with the above and below column? There's like,
Say that again.
so there's like, there's one page that went through like oscillation
Yep.
and then like the monotonic stuff,
Mm-hmm.
and then there's like above and below.
Bounded above and bounded
Yeah,
below.
above and below.
Are there questions on that, or are you just
I
wondering?
was just curious, I didn't know what,
Yeah, so if we got a little bit further into kind of the analysis of this, you have a sequence, and you could have a sequence, let's say here's 1, 2, 3, and so on. And you have a sequence that, let's say, is bounded above, and it's monotone increasing. Okay, so let's say that this thing is increasing, but you know that it's bounded up here. So if I start increasing, it may never get there, but it can't go above it. So if I know that I have something that's increasing and it's bounded above, it has to converge. It can't diverge if it keeps going up. Now, if you don't know that it's monotone, then all bets are off because it could oscillate or something. It could do kind of this sort of thing and never converge. But if you know that you're monotone increasing and you're bounded above, then it has to converge. Maybe it converges just to that bound that's above it, but it could converge to something smaller, but we know it has to converge. I think that that's kind of the main point that they're trying to make in that section, is that monotone functions, either always going up or always going down, that are bounded converge. So in this case, you just need bounded above because it's going up. But if I didn't tell you if it was going up or down, I just said it's monotone. And then you said, hey, it's bounded. Then we could say, hey, that's great, it converges. Does that make sense? Cool. Let's see, somebody said something here. Number 54. Best. Okay. Number 54. So plot a graph of the sequence a sub n for a sub n equals that, and then determine if the limit of the sequence, or explain why the sequence diverges. So plot a graph of the sequence a sub n for a sub n is equal to -1 to the n times n divided by n plus 1. Then determine the limit of the sequence, or explain why the sequence diverges. All right. So I suppose just writing out a few terms of this sequence might be helpful to us just to kind of get a feel for it. So if n was 1, what would we get? So I guess we get a negative from this thing. Then we get 1 over 2. So we get -1 over 2. If n is 2, this becomes positive and we get 2 over 3. So just 2 over 3. Then we get -3 over 4. Correct? Then +5 over 6, -6 over 7, +7 over 8, and we get the idea. Now, if these were all positive, is this going somewhere? Yeah, if they were all positive, what would this be moving towards? 1, right? So if they were all positive, it's getting closer and closer to 1, but it is not. It's bouncing back and forth. It's kind of like the negative ones are getting close to -1, and the positive ones are getting close to 1. So it is actually oscillating closer and closer to both -1 and 1. So we would say that this guy diverges by oscillation, actually, if we need such a thing. What does it ask for? Yeah, or explain why the sequence diverges. It diverges because in some sense, it's getting close to both +1 and -1. So it diverges by oscillation. Yeah.
So can an oscillating function converge?
It depends on how it's oscillating. So typically what I think of as oscillating does not converge. It just depends on kind of how you define oscillation, because like if you're oscillating, like you're getting close to, like in this case, you're kind of bouncing back and forth close to 2 values, then certainly that diverges. What if, the question is like, what if I was doing this sort of thing and kind of getting close to something? The question is that actually oscillating? I would say no, it's not. Because there aren't 2 things that the sequence is sort of getting close to. There's only 1 thing. So that's not really oscillation. It's just kind of like wiggling around that limit value. Does that make sense? So I would say if it's officially oscillating, no, it does not converge. Yeah.
I was just going to say that 55 was what we had before. Like I was going to say it oscillates. We just did that problem. But
Yeah.
And based upon what you're saying, it doesn't oscillate.
Yeah, it doesn't really oscillate. To me, oscillation means that you could find multiple things if you kind of like cut some, like if I cut every other guy out of this thing, then I would say, hey, it looks like it's going to hit 1. It's going to converge to 1. Or if I cut all the positives out, I'd say, hey, it looks like it's going to hit -1. That to me is oscillating. It's looking like it's going to multiple places at the same time, not just 1. So even though it's bouncing back and forth on either side in like 55, it's all of them are approaching the same value. So that to me is not an oscillating sequence. Yeah.
Can I go backwards or like into negatives? It looks like it's going bigger to small. Well, no, small figures, but what if it the other way?
So what do you mean by the other way?
So like, it seemed, never mind,
No, it's good. I think I know what you're saying. Are you saying more like if it went like a half, negative a third, positive a fourth, negative a fifth, positive, maybe not.
so like if it's, so if it starts off small and gets bigger, so it's like oscillating between like 1 and negative 1.
Yes.
Then wouldn't the other way be oscillating, like converging to a point because it's getting from small to big?
I see what you're saying. So if you're going like looking at this
Yeah.
direction, the problem is that like, okay, if you are looking at it this direction, it has to keep going.
Mm-hmm.
And like, what's next? Yeah, it would be like 0 over 1, which isn't so great. And then it would be like negative 1 over 0 or something, which, so it kind of breaks down looking at it this direction because all these ends are integers. So yeah, it's hard to look at it going that way. Other questions? Yeah.
25?
25. Yeah, let me. 25. So we've got ln of n squared over ln of 3n. So ln of n squared over ln of 3n, and we're trying to find, this was what number again? I'm sorry. 25. Okay. Okay, so we're just trying to find the limit. So we have the limit as n goes to infinity of ln of n squared divided by ln of 3n. Okay, so how do we want to think about this? Certainly as n goes to infinity, the top goes to infinity and the bottom goes to infinity. So we could think of this as a L'Hopital's rule problem, and I think in this case, thinking of it as L'Hopital's rule will be helpful. Okay, so we're taking the limit of kind of an infinity over an infinity. So I could just take the derivative of the top and of the bottom, and it should be the same thing. So the derivative of natural log of n squared is the derivative of n squared, which is 2n, over n squared. And here the derivative of ln of 3n is the derivative of 3n, 3, divided by 3n. Okay. So I can simplify that a little bit. This is the limit as n goes to infinity. On top, an n cancels, and I have 2 over n. On bottom, a 3 cancels, and I have 1 over n. So this is the limit as n goes to infinity. And of course, this is just 2 over n times n over 1. N's cancel, and I get 2. So yeah, L'Hopital's rule saves the day on this one. Let's see what else we got here. Yes.
I suppose we could have attacked that problem very similarly to the one beside it and just divided by, well, you could have pulled out the ln squared and pulled out the 2 and made it 2 ln.
You could have made it 2 ln of n.
And then you could have divided by, or multiplied by 1 over ln over 1 over ln, which is just multiplying by 1.
Say that again.
You could have multiplied by 1 over ln and all of that over 1 over ln. which is,
I suppose, but then you got ln of 3n over ln of n.
right, but can you do like, ln 3 plus ln? No, ln of n, is that a legal thing to do with logs?
You've got to be a little careful. So, yeah, how do you want to write ln of 3n? Now, ln of n cubed is nice because the 3 comes out, right? ln of 3n.
Can you write it ln of n plus ln of 3?
You could,
Okay,
yes.
and then from there, you multiply it in, and you can have 3 over ln, and then ln over ln on the bottom, and then on the top you would have 2 ln of n over ln of n, and then you could just, divide those and cancel.
So what's being said here is we could write this as limit as n goes to infinity of 2 ln n over ln n plus ln 3. Because adding natural logs is like multiplication, right? So the question is, now would it work to just divide the top and the bottom by ln of n? Very well may. So if we took the limit as n goes to infinity, and I divide the top and bottom by ln n, then I'd get 2 ln of n over ln of n divided by ln of n over ln n plus ln 3 over ln of n, which is 2 on top, and on the bottom I'd get 1 plus ln of 3 over ln of n. We're still taking the limit as n goes to infinity, and of course ln of infinity is infinity, so this thing goes to 0, and I get, whoa, did I just get 2?
Yeah.
Is that what I got before?
Yeah.
Oh, good. That's a good thing then. Yeah, it would work the same way.
Yeah, it's what you did over to the right.
Yeah, it is. I just wasn't, the key there was you got to kind of split this, right?
Yeah, you can't
Into
divide.
ln n plus ln 3, and then it works out. Yeah, either of those ways are good. Any other questions? This isn't a terribly hard section in some sense because it's kind of a repeat from Calculus 1. It's just limits as x goes to infinity, so to speak, except now we're doing sequences instead of functions. Next section, things start to get more interesting. We start talking about series, infinite series, where we're adding up an infinite number of numbers. And I talked a little bit about that last time, but kind of the classic example, there are a couple of classic examples actually, but one of them would be, I think, like the ant that's crawling across the table. And every day the ant goes halfway of the amount he has left to walk. Okay, so the first day he walks half the table. The second day he walks half of what's left, which is a fourth, correct? The next day he walks half of what's left, which is an eighth. The next day a 16th. The next day a 32nd. And he keeps on walking. So you're adding up infinite number of distances, but what do they all add up to? One table, right? So if he walked forever, he would have, so to speak, walked one table. So a really easy misconception to have when you go into infinite series and basically adding up infinite number of numbers is you want to say, well, come on, if I add up an infinite number of positive numbers, it's going to be infinity. And it's like, nope, it isn't. Because that's a great example just right there of adding up an infinite number of numbers, a half plus a fourth plus an eighth plus a 16th plus a 32nd, go on forever, and it adds up to 1. Yeah.
Why?
Why does it add up to 1?
Yeah. How can so?
Well, if you think about it, it does make sense in in the case of the ant? Tell me if you disagree or if I need to explain better. Like, okay, you've got this whole table and he walks a half of it. Then he walks a fourth of it and he's here. Then he walks an eighth of it and he's here. Then a 16th, then a 32nd, then a 64th, and so on 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 and so on. And if you add up all of those together, he certainly didn't walk infinitely far.
Yeah.
So he just walked one table.
So like at what point does it get?
So
Sorry.
yeah, so when would you get infinity?
Yeah,
Well, certainly here's a very easy thing, but no, I mean, worth saying that, well, what if you walked 1 plus 1 plus 1 plus 1 plus 1 plus 1? So how would you say to me that, oh yeah, you would walk infinitely far if you added 1 plus 1 plus 1 plus 1 plus 1? Well, the way you could say it is like, okay, will you walk more than 100? Let's say you're walking a foot at a time. Would you walk more than 100 feet? Yeah, just go 101 steps and you would. Or would you walk more than 1,000 feet? Yeah, just walk 1,001 steps and you would. So if you could tell me that in the first N steps of this process, you would go further than any number you want, then it's going to infinity. And so it's really interesting because like this is a very simple infinite series that I described with the ant, but it adds up to something. But I could also describe a very simple infinite series that doesn't add up to something. Now, 1 plus 1 plus 1, that obviously adds up to infinity if you added infinite ones. But some things are not as obvious, but they still don't add up. Like the most famous one, and I'll talk more about this one hopefully next time, would be the sum in going from 1 to infinity of 1 over n, which is 1 plus a half, plus a third, plus a fourth, plus a fifth. And it's confusing because these are getting very, very small, right? So you're kind of like, these are going to 0, so come on, it must add up to something. It does not. That's infinity. It diverges. So just because the numbers are getting small doesn't mean it adds up to something, but sometimes it does. And so when it does, we say it converges. When it doesn't, it doesn't. Another like great example, is anybody familiar with any honor students in here? Have you guys talked about like Zeno's paradox? Okay, too bad. But so Zeno's paradox, has anybody heard of this before? It's kind of the story of Achilles and the tortoise. So so Zeno submitted this problem that, you know, Achilles is going to race the tortoise, but Achilles is pretty fast and the tortoise is pretty slow. So let's go ahead and give the tortoise a head start. So the tortoise, let's say they both start here and this is Achilles and this is the tortoise. He said, give the tortoise a head start. So the tortoise moves up some amount. And then Achilles starts running. But by the time Achilles gets to this place, the tortoise has moved up a little bit, right? But by the time that Achilles gets to this place, the tortoise has moved up a little bit. And by the time that Achilles gets to this place, the tortoise has moved up a little bit. And so on to infinity. And so Zeno said, so how can Achilles catch the tortoise? If every time he gets to where the tortoise was, the tortoise has moved forward. You could make the same argument about if I have to walk out that door, then I have to go halfway there. But as soon as I am halfway there, I still have to go halfway there. But as soon as I get halfway there again, I still have to get halfway there. So how can I exit the door? Yeah.
You're talking about something that's not continuous. You're talking about that you measure like each individual measurements.
Uh-huh.
But if you, but like you can get to the door, so if you let those measurements go to infinity, then you reach the door.
So to speak. So this is just an interesting thing to talk about. There's no like right answer, so to speak. Obviously, we get to the door.
Right.
We know this, right? I can, in fact, walk out the door. But how can I, if I have to take all the, well, what, all these halves to get there? How many halves do I have to make to get there? Infinite. What happens, though, is you make those halves faster and faster. So like the first half, it might take me 3 seconds to get halfway there. But then it only takes half that much time, and then half that much time again, and half that much time again. And somehow the convergence of the time it takes adds up to a number. So I cover infinite halves in a finite time because those halves that I'm taking take less and less time, and the time taken converges. Sound like fun? Okay, this is actually kind of an important concept when it comes to different things. Let's say in engineering, some of you might be engineers or something, but let's say that you have a sensor on a fan. Okay, so you're trying to cool, let's say, some supercomputer, and you have a fan that does the cooling for you. So what can you actually tell that fan? And you need the supercomputer to be like, let's say exactly, I'm making stuff up, but let's say you wanted it exactly 80 degrees all the time. Okay, what exactly can you tell the fan? Like, you can't talk to it and say, hey fan, it would be really great if you just kept this supercomputer at exactly 80 degrees. But maybe there is a little bit of temperature variation in the room. So it's not just like the temperature's fixed in the room. The fan has to account for it. So how do you tell the fan what to do? Well, typically you use a sensor, right? And what can happen is you use a sensor and you say, okay, it's 81 in the room. So what should the fan do? Yeah, slow down. Speed up. Yeah, fans make things cooler. Okay, so it should speed up, right? So you tell the fan, please speed up and cool more. So it does. But what if it's like, okay, now it's 80.5 in the room? What do you tell the fan to do? Now, when you tell it to speed up, how much do you tell it to speed up by? And can you even tell it to speed up by all amounts in like the continuum? So you cannot. But the key here is that it is possible that you could come across a situation where you're saying, okay, I need to hit 80 degrees with the fan. And what I say is, okay, right now the temperature's up here. So I tell the fan to speed up. It does. It goes down. Then I tell it to speed up again. It goes down. It goes down. It goes down. But it converges to something that is not 80 degrees. That can happen. And this is how things fail, right? It's obeying you. It's making it cooler in the room every time you tell it to go down, but it never gets to where you need it to go. Or you could have a situation where you tell it to go down and then it jumps down here. So you tell it to go up, so it jumps up here, and then it goes down here and it oscillates back and forth, which also could be a bad situation because you need to keep the temperature constant. So all of these are actually problems that occur because of an infinite series. You're giving commands over time, and those commands are adding or subtracting a little bit from whatever it is you're doing. Maybe in this case, the number of RPMs on a fan. But does that mean it will converge
to what you want it to converge to, because unfortunately you cannot tell the fan, I want 80 degrees, right? You can't say that. So you have to be able to have it narrow in using like an infinite series, basically, on the right thing. And is that possible given the controls that you have in place? Those are problems that engineers get to deal with. Now, engineers have kind of come up with some tricks. I'm not the expert on that. You should talk to like Chad Stillinger or something if you want to know more about control systems and how to like narrow in on your desired temperature or distance or whatever the case may be. But you have to understand that the problem that's occurring is you have an infinite series that is not converging to either it's not converging at all or it's not converging to what you want it to converge to. Both of those are problems. And so sometimes, you know, when we start talking about infinite series, I kind of get the question of like, do these things even matter? Like adding up infinite number of numbers? This seems kind of just like ridiculous, fun thinking stuff, but does it really have real world application? And the answer is, yeah, it does. It has a lot of real world application. And if you don't understand what could happen with an infinite series, then you're kind of destined to get it wrong. Okay, that doesn't mean that you necessarily ever would calculate the precise infinite series that's going on, but understanding that something can always be increasing, but never get to what you want it to get to is important. Those ideas are important. Okay, that's good enough for today, I think. I think everybody's ready to do the homework over 10.2. So that is due tonight at 11. And then we will be covering section 10.3 on infinite series on Monday. So have a great weekend. I will see you then.